In this tutorial, we will see how to perform the calculations related to the Basic Economic Order Quantity Model, also known as the EOQ model. The economic order quantity is the order size that minimizes the total cost of inventory. Under the basic EOQ model, there are no quantity discounts. So, it is the order size that minimizes the total stocking cost as well. The optimal order quantity, Q star, equals the square root of 2 times the annual demand times the order cost quantity divided by the annual holding cost of 1 unit. 3 notes are in order. First, the 2 in the formula is always a 2. Second, some textbooks use Q sub OPT, short for optimal, or Q sub OH in place of Q star. Regardless, the formula is the same. Third, total stocking cost is generally calculated as part of these problems. Those calculations were covered in a prior tutorial. The number of orders per year is calculated as the annual demand divided by the optimal order quantity. There is no need to round this to a whole number. The order cycle is the inverse of the number of orders, the optimal order quantity divided by the annual demand. The resulting number is a fraction of a year. You multiply it times the number of working days per year to express the value in days. A company wishes to know the optimal order quantity for a particular item in inventory. They use 10,000 a year. It costs $55 to place an order and $20 to hold one item in inventory for 1 year. This company operates 250 days a year. Calculate. 1. Optimal order quantity. 2. Total stocking cost. 3. The number of orders per year. 4. The length of the order cycle in days. The optimal order quantity is the square root of 2 times the annual demand of 10,000 times the order cost of $55 quantity divided by the holding cost of $20. That equals 334.52. It is fine to round this result to a whole number, although we will not do that this time. We will, however, do that the next time so you can see the slight difference it makes. Next, we calculate total stocking cost. This was covered in a prior tutorial if you need to review. The total holding cost for the year is the order quantity of 354.52 divided by 2 all times the cost of holding 1 unit in inventory of $20. That equals $2,345.21. The order cost for the year is the annual demand of 10,000 divided by the order quantity of 234.52 all times the cost of 1 order of $55. That equals $2,345.21. These two values sum to $4,690.42. Notice that the annual holding cost and annual order cost are equal. This will always be the case at the EOQ and production EOQ points. In one of the total cost tutorials, I pointed out for one example that the order quantity was not optimal. These two values not being equal is how I knew. Now, had we rounded the order quantity to a whole number, these two values would not be exactly equal. However, they would be very close to one another. The number of orders per year is just the annual demand of 10,000 divided by the order quantity of 234.52. That equals 42.64. This number should not be rounded to a whole number. The order cycle is the order quantity of 234.52 divided by the annual demand of 10,000. That equals 0.0235. That should not be rounded since it is a fraction of a year. To convert that to days, we multiply times 250 working days per year, and that equals 5.86. So, each order of 234 meets their needs for 5.86 working days. A company wishes to know the optimal order quantity for a particular item in inventory. They use 8,500 a year. It costs $100 to place an order and $12.50 to hold the item in inventory for 1 year. The company operates 360 days a year. Calculate 1. Optimal order quantity. 2. Total stocking cost. 3. The number of orders per year. 4. The length of the order cycle in days. Since you've seen an example already, let me suggest that you pause the video and try to work this problem on your own. Once you're done, you can use the video to check your work and spot any mistakes you might have made. Plugging in the annual demand of $8,500, the order cost of $100, and the holding cost of $12.50 gives us an order quantity of 368.78. We round this value to 369. Plugging in the order quantity of 369 and the holding cost of $12.50 gives us an annual holding cost of $2,306.25. Plugging in the order quantity of 369 and the order cost of $100 gives us annual order cost of $2,303.52. These total to $4,609.77. The annual holding cost and annual order cost are close but not equal. That is because we rounded the order quantity to a whole number. Had we left it as a fraction, they would, in fact, be equal. Since you cannot order fractional units, rounding to a whole number is fine. Plugging in the annual demand of 8,500 and the order quantity of 369 gives us 23.04 orders per year. Plugging in the annual demand of 8,500 and the order quantity of 369 gives an order cycle of 0.0434. Multiplying that times the 360 working days gives us an order cycle of 15.63 days. While I will not narrate this example in any detail, a third example is shown on the slide. Using this data, calculate the optimal order quantity, total stocking cost, the number of orders per year, and the length of the order cycle in days. Since you've seen an example already, let me suggest that you pause the video and try to work this problem on your own. Once you're done, you can use the video to check your work and spot any mistakes you might have made. Plugging in the appropriate values, we have an economic order quantity of 20,412, total stocking cost of $3,061.86, 6.12 orders per year, and an order cycle of 58.79 days. If you found that this video helped you with your operations management problem, please consider liking the video and even subscribing to the channel.